Not sure, it doesn't say. So it's 6.2. Okay, so enthalpy is a state function. Now, let's define a state function. What is a state function?
H equals E plus PV.
What's a state function? What does it mean for something to be a state function?
It's like defined as the state of gas, state of
Oh wait,
It doesn't matter how you get there. Remember? The pathway doesn't matter, okay? So we're going to talk about enthalpy as in terms of energy, pressure, and volume. Okay, so H is equal to E plus PV. E being internal energy of the system, so you're talking about the system here, right? P is the pressure of the system, V is the volume of the system. Now, we're not going to use this as it is, but you'll see how this is going to relate to the Q that we were talking about earlier. Okay?
what Q?
Q, heat.
so enthalpy is like a state function?
Yeah, enthalpy is a state function. It doesn't matter how you get to the end result. The pathway from reactants to products doesn't matter. You look at the reactants, you look at the products, and then you look at the difference in energy. Okay, so it doesn't matter if it took 5 steps, 3 steps, 7 steps, makes no difference. Okay, because you look at beginning and end. So at constant pressure, as long as pressure is not changing, delta H is Q. What's Q? Heat, right? So when we're measuring delta H, we're really also measuring heat, and you're going to see how that is used interchangeably. And that works for constant pressure. So for a chemical reaction, delta H is the products minus the reactants. Okay, so delta means what? What's delta? Change, right? So the change of, bless you, energy of the product minus the reactants. That's why it doesn't matter how you go from the reactants to the products, because you're just looking at what the delta H of the reactants were and what the delta H of the products were. Okay?
Well, if you do it in the inverse, you do the reactants minus the products, you have to put it on the value.
No, it has to be products minus reactants. Like final minus initial. That's what delta is always. No. Alright, so if the H of the product is greater than that of the reactants, what kind of delta H do we have? Positive or negative? Positive. Positive delta H means what?
Exothermic.
Endothermic.
It absorbed. It took it in.
You have 50-50.
Right?
Yeah.
So it took it in.
Does that
So this indicates whether you're dealing with an endo or an exothermic reaction. So if delta H ends up being positive, I'm dealing with an endothermic reaction because the products are higher energy than the reactants. So that means that uphill process happened. Remember we talked about the uphill, right? So they end up with a higher energy. Yes.
would this, if it's positive, would it also mean that the surroundings is doing work on the system, or is that, like, when do you use that concept?
That concept works for delta H or Q.
Okay.
Right.
Would they have to ask you that?
Yeah, pretty much.
Wait, if you're saying that delta H is the constant heat, can we not do so would it not also be QP?
We're gonna look at the Q and the
Well, QP
and the pressure.
equals H product.
We're gonna look at it in a minute. We're gonna look at how they're all related. Okay, so what about the reverse? What if my products are of less energy than the reactants? Exothermic, right? Because now that it becomes a downhill process. Okay? So far, so good?
Yeah.
All right.
We're good.
All right, good, beautiful. So, 1 mole of methane. Methane is a very flammable gas, remember? You burn it at a constant pressure, and you end up with 890 kilojoules of energy released as heat. So what would be the delta H for this process if you had 5.8 grams sample of methane? How would you solve a problem like that?
You take 890 and then divide, like, so you do 1 mole of methane has X amount of grams. Let's say it's 20. So if it's 20
60.
grams, you take 5.8, divide it by 60,
Mhm.
and multiply that by 890.
Yep.
Wait.
890 kilojoules is
Wait,
the
60?
molar enthalpy. Okay?
Wait,
So,
no, it should be 20.
molar enthalpy means that it's the amount of energy used, released, absorbed, whatever it may be, per mole of the product, right? In this case, its molar enthalpy of methane is 890 kilojoules, and methane is 16 grams per mole because carbon is 12, hydrogen is 1, da da da. So there you have it.
You get 322. Yeah, 0.62.
320, yes. Now, positive or negative?
Negative.
Why?
Released.
Because it said it released. And plus, it's burning of methane. I hope there's heat being released. Okay?
So it's the energy released, right?
Mm-hmm.
And because it's released, it's negative over the moles of. But why does it say the moles of?
Oh, you're
So,
trying to get the
The
heat
890 is per mole,
Okay.
right?
Okay.
So since 5.8 grams happens to be 0.36 moles, right? So it's 0.36 of 890
So you
because
multiply-
890 happens for 1 mole. So you multiply the moles.
moles
Yeah.
by the.
Because it's molar enthalpy. When they say molar enthalpy, when they give you units, they give you kilojoules. They don't say per mole. You have to assume it's per mole.
Okay.
Okay? So that keep that in mind because a lot of problems happen that way.
Is that because
Not always.
if they say
We'll talk about it.
grams, like if they say 5.4 grams, could you assume that they want you to convert it to moles? Like,
If you're dealing with molar enthalpy, yeah, pretty much. So heat flow, right, negative 320. In this case, when you burn the 5.8 grams, you're going to get 320 kilojoules of heat released. Okay. So let's look at this one. Overall reaction in a commercial heat pack is iron plus oxygen gives you iron oxide. And this reaction releases negative 1,652 kilojoules of energy. It says if I have 4 moles of iron, right, a whole bunch of oxygen, so excess oxygen, doesn't matter, how much heat is going to be released? That much,
Why
right?
Did you say
Why?
1650 and not 1652? Because it just says it.
I know.
I don't think
because
But-
that's the chain. That's the.
So that means that this is not molar enthalpy right now. This is the delta H for the reaction. So
Four
this
molar.
represents 2 iron oxides for Fe's.
So that is the molar enthalpy. The blue.
So it's
No.
Well, no.
The molar enthalpy would if you divided that by 4.
Right. For
Because
iron,
it'd be like per
yeah.
mole.
no, we're gonna be multiplied by 4.
No.
divided because that's already for... Okay, here you go. Here you go. Here you go.
Wait, in the previous
How much energy for 1 mole? Half that. Okay, so let's go back to the reaction for a second.
4.
Okay,
Yeah,
so...
but you divide it by
No, because that's the product.
Here,
not
let
the-
me rewrite this here. 4 moles of Fe. When it reacts with 3 moles of oxygen, I'm going to get 2 Fe2O3. Delta H happens to be negative 1,652 kilojoules. Okay. So now the question says, how much heat is released when you have just 1 mole of Fe2O3? So how much heat? Half of 1650, right? So that's why you get 826. How much heat is released if you have 1 gram of iron?
A fourth.
Oh,
A fourth of
so how
No,
would
it's
you?
not. It's
No,
1
no,
gram, not
no,
1
no.
mole.
Right, per gram.
So
So
then you have
how
to-
would I go to 1 gram? So what would I do?
Would you convert it to moles and from there?
1 gram.
I can first maybe get the molar enthalpy of iron,
and then use
right? So
that.
divide it into 4. So if I do 1652 divided by 4, that's going to give me per mole of iron.
Uh-huh.
And then I'm going to determine how many moles 1 gram is.
Exactly.
1 gram divided by 55.85. And then you get only like 7.39, which makes sense. Yes.
Why in this problem we're dividing for the molar enthalpy, we're dividing by the moles, but in the previous problem we were.
Because that one was already molar enthalpy. That one was already per mole. This one is per reaction. This, the 1652 is for this reaction. That means for 4 moles of Fe, this is how much I'm going to get. For 2 moles of Fe, that's how much I'm going to get. Does that make sense? Okay. How much heat is released with 10 grams of iron, 2 grams of oxygen reacting? How would I solve this problem?
find the.
Alright, take out a piece of paper.
Is it the limiting reaction?
Piece of paper out.
Oh, you can find which one's the limiting reactant first.
That's annoying.
No, it's not. It's fun. Alright, piece of paper out. Let's go, let's go. I want this solved step by step. I'm going to come around and check. You have, how about 3 minutes?
3 minutes.
Okay, 4 minutes. Because it's Thanksgiving, I'm being nice.
You love Thanksgiving.
I do love Thanksgiving. It's my favorite holiday of all.
I feel like you're that person that's already started cooking.
No, but my turkey is brining. I have a big giant. Okay, I'm gonna pause this for a sec. So, 10 grams of iron, 2 grams of O2, right? What do you do first? What was your first step? You first find which one is my limiting. Was it the iron or O2? Did everyone agree on O2?
I got it.
Everyone got O2. Okay. Now you know that O2 is your limiting. Wonderful. What's your next step?
You divide 1652 kilojoules.
Hold on to 1652 for a second. 2 grams of O2 is how many moles?
You put it divided by 32.
Okay.
0.06.
So 2 grams of O2, right? Divided by 32 grams of O2, what do I get?
0.0625.
625. Is that right?
Wait,
Did everyone get this?
yeah.
Okay. Now, what does that tell me?
You need
I need just enough kilojoules to deal with this many moles. Now, the 1650 that you saw here, let's go back for 1 sec. The 1650 here is for how many moles of O2? 3 O2s, right? So per mole, I only have like 500. So what am I going to do? Well, I'm going to take the 1652 and say that it's per 3 moles. And I just need it for 0.0625 moles.
Why did you divide it by 3?
Because, back to this,
302.
this reaction produces 1650 per 3 moles of O2. Not per mole. This is not molar enthalpy. It's the enthalpy for the reaction. The reaction has 4 moles of Fe, 3 moles of O2, and 2 moles of iron oxide. Right? So nothing is per mole in this case. Got it? Yes? All right. Beautiful. And so that gives me 34.4 kilojoules. Did you get 34.4?
Yeah.
All right.
Wait, is that just...
Wait, when we write,
Why is it
even though it's molar enthalpy, do you still just write kg?
Okay, this is not molar enthalpy. This is enthalpy of 2 grams. Right? It's not molar enthalpy. Yes.
Why is it 3 sig figs?
Because 2.00 is 3 sig figs, 10.0 is 3 sig figs. Okay? Ladies?
But I got really cute shoes and I found them on sale.
All right. Calorimetry.
I know you'd be sensitive to that. No, that's why.
All right.
Wait, are you gonna paint your nails like red or orange?
You should
for
make
fall?
little turkeys on them.
Red. We're going red.
All right. Science of measuring heat.
Do like every other red and orange. That's so festive and holiday spirit of you.
Calorimeter. What is that? It's a
Device
device.
used to determine the heat associated with the chemical reaction.
Which is the lab you'll do. Okay.
Burning.
There's a few different types of labs we do with this. We do the regular old reaction in a calorimeter, and we'll just use styrofoam cups for our calorimeter. But we also have the fancy ones that I'll show you what they look like as well.
You show us today.
Not the one with the Cheeto Puffs?
The Cheeto Puffs will do that one too.
Yeah.
That one just because it's so fun, so you can see all the oil burning and how disgusting it is.
Miss H.
What else did we burn? The Cheeto and the what?
Marshmallow.
I feel like Miss
so-
H
I
is
ate
trying
so
to make
many.
us like not eat anymore.
That's my goal. All right. Specific heat capacity. That's the heat absorbed per increase in temperature is your heat capacity. The specific heat capacity, now let's look at this. It's the amount of energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius.
Isn't this in the ocean or something?
The specific heat of water is like 4.18, which is really, really high specific heat. Water can take up a lot of heat before it changes temperature. That's why if you live by the ocean, you don't have these varying temperatures that you have in the valley, right? Like in the summer, we might have 105 during the day, and we have like 70 at night. That doesn't happen by the beach, right? Why? Because all that heat during the day is being absorbed by the water, and at night that heat is being released. And since the water is using its heat capacity to do that, you don't have these extreme temperatures that you have in the valley where you don't have water. All you have is a lot of concrete and asphalt.
And grass sometimes.
Occasional patches of grass, and now fake grass, which is even worse because a lot of water runs off when you have fake grass.
So hot. River.
And it hurts when you slide on it.
Oh yeah,
I like
it burns.
playing- I
Oh,
like
it's
playing
the
with turf.
worst.
Turf is so much better.
California
birds. Nothing bad happens. Like,
Yeah, that is true.
No, turf.
But turf is bad for runoff. They realized after they,
That's what it is.
put all the turf in, they're like, oh, wait a minute. No, we're not going to fund the turf. Let's make sure that your front yards have enough plants and roots so that it can absorb water, because otherwise all you're getting is runoff. All right. Now, molar heat capacity, same concept, but obviously now you're dealing per mole. So you're going to get some different ones when you have the problem. So you have to always pay attention to what units are given to you and what it tells you in the problem, so you know how to convert properly. Otherwise, a lot of people make mistakes from there, from like not changing joules to kilojoules and things like that. Now, what's the difference? This is per mole. Let's go back and see what was the difference. This is per gram. Okay, per gram, per mole. Okay? So heat capacities of metals are different than that of water. It takes less energy to change the temperature of gram of metal by 1 degree than gram of water.
Then this where Avogadro. No, there's like a constant here.
All right, so this is a coffee cup calorimeter. This is what I mean by using just styrofoam cup, right? And we have a cover. You put a thermometer in there to see the temperature change, and you're carrying out the reaction inside the calorimeter, and you measure temperature change. Once you know what the temperature change is of the water, then you can easily determine your heat capacity, because you know the heat capacity of water.
Wait, so how do you find the heat absorbed from that?
We'll plug it in. Well, I'll show the formula. Heat capacity of water, liquid water, 4.18. It takes 4.18 joules in order to take 1 gram of water up by 1 degree Celsius. So imagine when you're boiling water, how long it takes to actually boil water, right? Because you have to get it to 100 degrees Celsius to boil it. That's why it takes such a long time for water to boil. Something like aluminum is only 0.89. Okay, mercury is 0.14. So it doesn't take a lot of energy to heat metals. And that should make sense to you. Why? Because metals are great conductors of heat and electricity, right? When you're cooking with the, metal pans, obviously they get hot really fast. That's why there's insulating handles. Okay? All right, let's take a break. So go to the restroom, do whatever you need to do. Okay, so the coffee cup calorimeter, just a styrofoam cup. You have water in there, you carry out a reaction, water absorbs the heat, you measure the change of the heat, and then you're going to plug it into a formula, which I'll show you later. And the delta H is really Q in this case. Okay, it's constant pressure, and whatever heat is being released or absorbed by the water is going to equal whatever heat is being released or absorbed by the reaction, which you'll see. So when two reactants are at the same temperature and they're mixed together,
Can you unhighlight it?
yeah, do that.
Thank you.
Exothermic reaction will warm the solution. The endothermic is going to cool the solution. right? So the water is going to cool if it's endothermic because heat is being absorbed by the reaction. Exothermic, the water is being heated up, or whatever the solution is, the surrounding.
Like the ice pack thing when it becomes colder.
All right, now let's look at the formula. In order to calculate this and determine exactly what's going on, in order to determine the energy released by the reaction, right, you need the specific heat capacity, which is S or C. You see it both ways. M is the mass that you're dealing with, and delta T is the change in temperature of your solution.
Before, not like that.
Q equals MC delta T.
Yeah, I have that.
Okay.
Like that.
C or S is specific heat capacity. Okay. The heat of the reaction is an extensive property,
Yeah, Q equals M.
and extensive means that it's dependent upon the amount, right? Because if you have more of the product, if you have more grams, if you have greater mass, then you're going to have greater heat. Okay, so it's dependent on how much of the substance you have.
So the specific heat is usually given, or would you have to do the other equation to get here?
It's given. Especially with water, it's pretty much a no. 4.18. Yeah, liquid water, 4.18 joules. Now, if you have 1 liter of 1 molar barium nitrate solution, that's 25 degrees Celsius, and you mix this with 1 liter of 1 molar sodium sulfate solution at 25, and in the calorimeter, the white solid barium sulfate forms, and temperature goes up to 28.1 degrees Celsius. Okay? So you see what's going on first?
Well,
So temperature changed by 3.1, right? And you added 2 liters of the solution.
don't you need to find the mass?
Wait, here.
Wait, was that
What?
formula was the same?
But you have to convert to.
Are you talking about this one?
Yeah, what was the difference? We did last year.
MC delta T.
It's the same thing.
Okay, now, here are some assumptions you have to make. The calorimeter itself doesn't absorb or release heat. You're assuming. Okay, so the calorimeter isn't doing anything, the solution inside it. Specific heat of water is 4.18 joules per degree Celsius per gram. Okay. Density of the final solution is 1 gram per mil because you're assuming it's pretty much mostly water.
Wait, do we have to convert it to Kelvin?
These are all per degree Celsius. Now you're going to calculate the enthalpy change per mole of barium sulfate that has formed. Okay, so where are we going with this? The goal is to calculate delta H, right? Delta H is really the Q. What do you have? Well, you have 1 liter of barium nitrate, you have 1 liter of sodium sulfate, you have a change in temperature, you have heat capacity of the solution, you have density.
You have
Okay,
to see-
do you really have everything to do MC delta T?
Yeah.
Really you do. Okay, first let's look at what is this reaction?
Do you leave changing T in Celsius?
Yes.
Oh,
Because all of their heat capacities are per degree Celsius. So, what is this reaction really? Well, barium plus sulfate gives you barium sulfate, right? Because that's the white powder that it's talking about, the precipitation reaction that forms. Since the temperature increases, this reaction must be exothermic, right? So then delta H has to be negative. So we're going to take the specific heat, the mass, and the increase in temperature and determine the heat of the absorbed.
How do you know that it's like barium plus sulfate? Because doesn't it give you the sodium sulfate?
Yeah, but then it says barium sulfate is formed. Right? The solid barium sulfate is formed.
So you just
So that's really all there is. But it doesn't matter for this purpose because it's really just about the mass.
Okay.
Wait, how do we know the heat capacity is 4.18?
Water.
But it isn't water.
It is water.
It's barium.
They're all aqueous solutions. It's water. It's really just water. It's a whole bunch of, it's
So the fact that it's like
an
sodium-
assumption again that you're not really worrying about the other ions making a difference because you're assuming those changes are not really much.
Is it because it's sodium sulfate that's actually water, so you don't need to calculate the sodium in the equation? Is that what it is?
Well, sodium sulfate is a soluble solution, right? And then the sodium doesn't do anything in the reaction,
Okay.
nor does the nitrate, really, right?
Yeah.
That's the barium and the sulfate that come together.
So you should look at what's formed in order to form your equation.
Okay, so how many liters do you have? Well, you had 1 liter of each solution. That's 2 liters. 2 liters, you're assuming that the density is 1, so that's really 2,000 grams. Okay, how do I know that? Well, I know density is 1 gram per mil, and 1,000 milliliters is a liter. Okay, so for my densities, unless it tells me otherwise, all my densities for these are the density of water, which is 1. Okay, because the differences with those ions in there are so tiny that unless you're doing some crazy accuracy experiment, it doesn't matter for your purpose.
Now, why do you need to do the net ion equation?
You don't.
I don't know how to do it.
You really don't. So, you're looking at 2 liters of solution, 2,000 grams. Temperature change is 3.1 degrees Celsius, right? And it's 4.18 joules per degree Celsius gram. That's specific heat. So the heat that is released is 2.6 times 10 to the 4 joules of heat. So what is Q? Well, Q and delta H are the same thing. It's negative 2.6 times 10 to the 4. Why did we all of a sudden put negative there? Temperature changed. It increased. That means what kind of reaction was I dealing with? Exactly. Exothermic. So that means heat was released into the solution, right? So the reaction happened. It heated up the water in there. That means that it is an exothermic reaction. So the delta H molar enthalpy is negative 26. Now, here's when you need the reaction.
How do you know that it's negative 26?
Hold on. This is where you need the net ionic to make sure that this that you solve for is per mole. Okay, so you don't really care about the reaction to solve it. You care about it when it asks you, well, what is it per mole, right? You want the molar heat of formation of barium sulfate. So the delta H is negative. Now, why was it negative again? Exothermic, right? And it's joules per mole, but if you want to convert it to kilojoules, you just divide by 1,000. Yes?
How do you know that negative 26,000 is negative 26 kilojoules per mole? Like, how did you change it? Like, are you just supposed to know that if you,
Joule to
divide
kilojoule
by
is 1,000.
What?
1,000. Kilo is 1,000, right?
You divide by 1,000.
Of course. Any kilo is 1,000.
Not kilo.
Yes.
Oh, never mind.
Yes. Alright, so that was constant pressure calorimeter. Then we have constant volume calorimeter. These are used in conditions when experiments they have to be done under volume that cannot change. But no work is done since volume must change for PV work to be performed. So bomb calorimeters. Bomb? Yeah, bomb. Like boom, bomb. Boom. You weigh the reactants and they're placed in a rigid steel container and you ignite them.
Ready to know these?
And the change in energy is determined by the increase in temperature of water in other parts. It's still the same thing, contained within a steel container, and you ignite the reaction within the container.
Why is no work done?
Because PV, V is not changing, that's 0.
Okay.
So, this is what the bomb calorimeter looks like.
Can we make one?
No. Alright, so you have ignition wires. Okay, you're doing this in a closed container. You're burning this, exploding it, whatever it is you're doing. This is the steel bomb. This is the insulating container. There's water. You're still changing the temperature of the water. You're still measuring the change of the temperature of water by having the thermometer in there. It's just that this is contained. Okay, it's a contained reaction because you can't change volume. Okay, the setup is different. Concept is the same.
So is the specific heat of water 4.18 or is it
Yes.
capacity?
Specific heat of water.
Because
Molar heat capacity. Yeah. Specific heat of water.
Is molar heat capacity the same thing?
Molar
Yes.
heat capacity is per mole. Yeah.
So but it's 4.18 grams.
4.18 joules per gram degree Celsius.
That's why it's specific heat.
That's specific heat.
You can convert it to the molar.
Yeah.
But it's saying specific heat capacity.
Right.
It's even more confusing.
Specific heat of water.
Okay.
It's all heat. It's really all the same concept, that it is a certain amount of energy required to change the temperature.
Is the heat capacity of
Calorimeter.
Yeah. Is that specific heat?
That's
Or is that molar heat capacity?
that's Q.
Is that specific or molar heat capacity?
Why does it say Q plus W?
Depending on what you're measuring.
Why?
Specific heat is usually a constant. Everything else you measure. Okay? Specific heat is dependent upon the substance. Like 4.18 of water is the specific heat of water. That doesn't change for water ever. Okay, so that means anytime you're heating up 1 gram of water by 1 degree Celsius, it's always going to take 4.18 joules. But molar heat capacity, depending on what you're dealing with, might change.
It says per gram, then you know specific heat.
Yeah. Specific heat is per gram. Yes.
Why does it say Q plus W?
We're going to look at that now. W is work. Yes? And we measured work as negative P delta V. But if it's a constant volume, what's your change in volume?
0.
0. It doesn't change. So then if it doesn't change, your delta E, that's Q plus W, is just Q. Right? So your energy is just your heat in this case.
And then what's Q?
Okay. Work is negative P delta V.
Isn't that
Yes?
Delta V is 0.
Delta V is 0. What's your work?
0?
W.
There is no work.
E.
You're not doing work if you're not changing volume. Therefore, E is equal to what?
Q.
Q.
Got it. Oh,
So then energy is released by the reaction. That's the temperature increase times the energy required to change the temperature. So it's delta T times heat capacity of the calorimeter. When you're only dealing with a calorimeter that is a constant volume. So bomb calorimeter, not the regular calorimeters that we use, which are the Calfee calorimeters.
So is that a constant?
No.
The
No.
calorimeter?
No.
So
Constant volume. That means when you carry out the reaction, volume doesn't change because it's all in a closed chamber.
to find the heat capacity, then how would you find it in the equation?
Alright, so let's say hydrogen gas can be obtained by decomposition of water, and you can use hydrogen gas as a substitute for methane. To compare energy of combustion of the fuels, the following experiment was carried out using a bomb calorimeter with a heat capacity of 11.3 kilojoules per degree Celsius. So it's given to you, right? The heat capacity is given. It's saying that's what it is. So if you had 1.5 grams sample of the methane gas, and it was burned, and there was a temperature increase of 7.3 degrees Celsius, and you had 1.15 gram sample of hydrogen gas burned, temperature increase was 14.3. Now tell me, is it more energy efficient to burn hydrogen or methane?
It's more efficient.
Remember the calorimeters? Heat capacity is 11.3 kilojoules per degree Celsius. And if I'm burning methane or hydrogen, what am I looking at? Well, let's see. Where are we going with this? The 1.5 grams changes 7.3 degrees Celsius, right? 1.15 grams changes it by 14.3 degrees Celsius. You know that the energy is delta T times the heat capacity of the calorimeter. In other words, does it matter how many grams I had to begin with? No. Okay. So all I care about is the temperature change and the heat capacity of the calorimeter. So in the case of combustion of methane, you only have 83 kilojoules. But if I'm combusting hydrogen, I get 55 kilojoules, right? Wait, no, sorry.
140.
55 is per 1 gram. So then I get 162. So per gram, if I'm going to compare it per gram, right, then I know it's 55 versus 141.
So hydrogen is more.
Obviously, hydrogen is a lot efficient in combustion, or a lot more exothermic, really.
How did you get this change in temperature?
It tells you. It just, yeah, it just said it right here. It says it's an observed temperature change of 7.3. The other one was 14.3.
Oh, okay.
It's really just a multiplication and getting rid of the units. That's all it comes down to. Okay? All right, next one is Hess's law.
Yay.
Before we do that, though, okay, so if you can, I'm going to pause this for now.